Okay, this is part 2 of solving quadratic trig equations, and now we're actually going to tackle a quadratic trig equation rather than just a linear equation. Our first example will just be solving when you have a single quadratic term. So our single quadratic term in this case is just this cos squared x. Notice we don't have just a cos x, just the cos squared x. So this would be like saying, I'm going to use this space up here, and I'm going to use y to represent cos. Y squared minus 4 equals 0. And by minus 4, I mean 2. So basically, you're just asked to solve this equation. And we can solve that equation by isolating for y squared, right? Adding 2 to both sides. You would get y squared, 4y squared equals 2. And then dividing both sides by 2, you would get y squared equals, but dividing both sides by 4, you'd get 2 over 4, which is the same as a half. And then to solve, you would square root both sides. And you would get y equals plus or minus, when you're square rooting, the square root of 1 over 2. So it's pretty much solved the exact same way, except instead of y, we have cos. So here we go. 4 cos squared x minus 2 equals 0. Add 2 to both sides, start isolating. Divide both sides by 4. 2 divided by 4 is 1/2. To start isolating for x, we'll square root both sides. And we get cos x on this side. And when you square root 1/2, the square root of 1 is 1. And the square root of 2 is root 2. And you get plus and minus. So basically, we end up in the exact same spot, except instead of y, we have cos. If you prefer doing the substitution because you don't like looking at the cos squared x and you just want to write y squared and solve, you can, and then at the very end you just pop cos x back in there and you've got the exact same thing. So now basically we're solving for where is cos squared, or cos x, where's cos x? 1 over root 2. And the nice thing is, 1 over root 2 is one of our special triangles. If we go from this angle, cos would be adjacent 1 over hypotenuse root 2. 1 over root 2 would give you this pi over 4. So where is cos x 1 over root 2? Well, it's when x is pi over 4. And if you did cosine inverse of 1 over root 2, or even negative 1 over root 2, you'd get pi over 4. So you'd come up with that angle. That angle is your reference angle, or your related acute angle, beta, and that's in all 4 quadrants, or in the quadrants where cos is positive. But in this case, it's positive or negative. So the question is, which quadrant is cosine positive or negative? Well, in quadrant 4, it's positive. In quadrant 1, it's positive. In quadrant 2, it's negative. And in quadrant 3, it's negative. So it's negative or positive in any of those quadrants. So your answers are going to be in all 4 quadrants. Where in all 4 quadrants? Well, where your reference angle is pi over 4. So in the first quadrant, that would just be theta 1 would just be pi over 4. In your second quadrant, that would be this angle with a reference angle of pi over 4. So that would be pi minus pi over 4, which is 3 pi over 4. So there's 2 of our answers. In the third quadrant, that would be pi plus pi over 4. Which is 5 pi over 4. And in the fourth quadrant's angle would be, the reference angle pi over 4, would be 2 pi minus pi over 4, which is, that'd be 8 pi over 4 minus 1 pi over 4, 7 pi over 4. So how are we coming up with all those answers? Well, Since when you square root a value, you get both positive and negative, you're going to get answers in 4 quadrants because the ratio we're looking for is both 1 over root 2 and negative 1 over root 2. You get 1 over root 2 for cosine in quadrants 1 and 4. You get negative 1 over root 2 in quadrants 2 and 3. So all 4 quadrants are going to give you an answer. This reference angle that you can solve for by doing cosine inverse or using special triangles is the reference angle for your answers in all 4 quadrants, just as it always is. That beta you solve for by doing cos inverse in every one of these trig equations, whether it's linear or quadratic, is your beta that you're using in all 4 quadrants. An angle in the first quadrant, theta is beta. Angle in the second quadrant, it's pi minus your beta. Angle in the third quadrant, it's pi plus your beta. And an angle in the fourth quadrant is 2 pi minus your beta. That's how we came up with all 4 of our answers. So solving a trig equation with just a single x squared term or cos x squared term, you have to look for 4 answers. And if there was compression, there'd obviously be even more answers. If there was stretch, there'd be less answers. And if the domain was different, there'd be more or less depending on what the domain is. But just in one rotation, and just with that one term, we come up with our 4 answers. That's one example of a quadratic trig term. That's just one term with a squared. In our second example, we have some sines and some coses. So let's take a look at this one. Why is this quadratic? Well, when you have sine and cos are both sinusoidal, and when you have sine times cos, you would have a squared function, which is quadratic by definition. So here we go. We have 2 sine x cos x minus sine x. What we have here is 2 terms. This 2 sine x cos x and this negative sine x. And we're looking for when it equals 0, between 0 and 2 pi. What we have here is we have a common term in both of these terms. Sine x is in both of these terms. So what we can do here is when we have that, we can do something called common factoring. We can common factor sine x. So what we have is instead of 2 sine x cos x minus sine x equals 0, we can common factor out sine x. And we're left with 2 cos x minus 1 equals 0. And now to solve this, you're looking for where sine x equals 0, and you're looking for where 2 cos x minus 1 equals 0. So now you're just solving 2 different linear trig equations. Well, sine x equals 0 is a critical value. That's where sine actually starts, because if you remember, I'll sketch it up here. The sine function starts at 0, 0, goes up, hits 0, goes back down, and hits 0 again. And those critical values are actually your answers for this part. x1, your first answer is, well, it starts at 0, so 0. x2, the second time it hits 0 is at pi. And x3, the third time it hits 0 is at 2 pi. So there's 3 answers right off the bat. Why are those 3 answers? Well, if you plug in 0, pi, or 2 pi into this expression, sine of 0, sine of pi, or sine of 2 pi is 0. 2 times 0 times anything is 0, minus sine of any of those numbers is 0. 0 minus 0 is 0. That satisfies the equation. Or in factored form, any of these values plugged in for sine will give you 0 as a ratio. 0 times whatever this works out to is still 0, so we have 3 answers from that expression. The second set of answers comes from this linear trig equation. And if you start isolating for x, you can solve that linear trig equation as well. Add 1 to both sides, divide both sides by 2. You're looking for where cos x equals 1/2. Cos x equaling 1/2 is one of the special triangle angles. In our special triangles, 1 and 2 exist in this triangle. Cosine of pi over 3 would give us our 1 over 2. So x must be pi over 3. And keep in mind that that is a reference angle beta. We're looking for where cosine is positive. Cosine is positive according to the cast rule in quadrants 4 and quadrant 1. So we're going to have answers in 4 and 1. In quadrant 1, If our reference angle is pi over 3, our graph's going to look like this. That's our reference angle. But also, that's our solution. Because in quadrant 1, theta equals beta. So our x is going to be pi over 3. And this is our fourth answer, so x4 is pi over 3. To get our last answer, we're looking in quadrant 4. In quadrant 4, I'll just draw it down here, your reference angle is still the same, but in quadrant 4 it's 2 pi minus beta to get your answer. So our x5 is just 2 pi minus pi over 3, or this angle. That's our x5. 2 pi minus pi over 3, that'd be 6 pi over 3 minus 1 pi over 3 is 5 pi over 3. So there is our 5 answers. 2 coming from our second factor after common factoring, and our first 3 answers coming from our first factor after common factoring. Sometimes it's hard to see the common factoring. So what you could do is you can do a substitution and say, let sine x equal a and cos x equal b. Then your equation says 2ab minus a equals 0. And then start isolating for variables, which you can't do because there's 2 variables, so you can factor to isolate. And by factoring, you see a is common to both terms, so you got a, and that would leave you 2b minus 1 equals 0, and then replace back with your sines and coses. Sine x equals 2, cos x minus 1 equals 0. And now you're just solving each of these set equal to 0. And those are just 2 linear expressions, and we know how to solve linear equations. Okay, that's it for video 2. In video 3, yes, there's a third part, we're going to do, this isn't going to be a practice question, it's going to be an example. So we're going to do example 3.5 and example 4, which is solving 2 different types of trig equations, quadratic trig equations. Thanks for watching, and I'll see you next time.